This is AQA Statistics, Continuous Random Variables 5. This video is about the exponential distribution, when to use it, and its probability density function. Please pause a moment to read the slide. You've already learned about the application of the Poisson distribution to discrete events. The exponential distribution is another way of modelling the same process. Here we look at the continuous interval of time or space between successive events, remembering that events occur singly. The same parameter lambda is used for both distributions. Please pause a moment to read the illustration. Here we have random vehicle arrivals to a traffic checkpoint. The parameter lambda, the constant rate of random arrivals, is 8 per minute. Remember, this means the expected value of x is 8. The time interval between arrivals is modelled by the exponential distribution with the same parameter 8. Pause the video to think what the mean inter-arrival time might be. The expected time interval between successive events is 1/8 of a minute, or 0.125. Now we'll have a look at how Poisson and exponential distributions reflect different aspects of the same process. Continuing the same example, where we are modelling arrivals using the exponential distribution with parameter 8, here's a sequence of random arrivals that have been sampled from that distribution. And we can see two things going on here. We can see that there are individual arrivals with times in between those arrivals. Now, it is those times that are distributed according to the exponential distribution. But also, it is possible to look at each minute in the first 5 minutes and consider how many arrivals there have been. And that would be looking at it as though it were a sample from Poisson 8. So in this sample, when we consider the inter-arrival times, we find that the mean inter-arrival time turns out to be 0.13 minutes compared with lambda of 0.125. And in each of the first 5 minutes, we see that the sampled number of vehicle arrivals, 8, 8, 10, 7, 8, compares with Poisson 8, which is the underlying distribution. Please pause for a moment to read the new example. Now, a suitable model for the number of customer arrivals per minute, number of customer arrivals, is going to be Poisson 1.25. A suitable model of the time between customer arrivals, now that's going to be exponential 1.25. The expected time interval in minutes between customer arrivals at the cash point, now that is going to be 1 over lambda, which is going to be 1 over 1.25, which equals 0.8 of a minute. Please pause a moment to read the example and answer the questions. Now here the expected value x between butterfly sightings, as the distance in meters, is 5. So if the distance between sightings is 5 meters, the number to be seen per meter now, this is going to be the value for lambda. I guess what we need to remember is that here what we're looking at is 1 over lambda, which is 5, and here now then we've got 1/5, which we could write as 0.2. Suggest a suitable model for the number of butterfly sightings per meter. That's going to be Poisson 0.2. Okay, there we are. An important feature of the exponential distribution is that it has no memory. This means to say that the time interval until the next event is independent of how much time has already passed since the previous event. Let's look at an example. We're still considering the butterfly walk. Please pause to read the example and answer the question. The exponential distribution has no memory. Now Ian has not seen a butterfly for 6 meters. However, this is irrelevant when we look forward. So to consider how much further he can expect to walk, then we simply have to consider this expectation value here. And so the answer is that Ian can expect to walk another 5 meters. Okay. In the next slide, we're going to take a look at the PDF for the exponential distribution. Here is the PDF for the exponential distribution. First thing to note is that the function here is non-zero only for t greater than or equal to 0, and when t is less than 0, the function itself is 0. And it's important to remember that t now is a continuous random variable, such as time. It could be distance. Here we have a requirement to show that the PDF meets the conditions, show that f of t meets the conditions for a PDF. The second part of the exercise is to make a sketch of the PDF. Here's a quick recap of the conditions for a PDF. Firstly, that the PDF must take a value that's greater than or equal to 0 for all values of the random variable. The other condition is that the total area under the PDF must sum to 1, as it represents the total probability. Your sketch of the PDF looked a little bit like this. So if we just fill in some key features, here's where t is 0, and here we are, there's the t-axis. Then f of t is up here. And the point of intersection of the graph with the vertical axis is lambda there. Note that the curve is asymptotic here to the t-axis. Now, since we've got this for t less than 0, then we've got f of t equals 0, and for t greater than 0, we've got this function, but which is asymptotic and therefore always greater than 0. We do meet that condition, actually, that f of t is always greater than 0. Okay, so we're definitely meeting that condition, greater than or equal to 0. And we now need to just check that this total area under the graph here, should add up to 1, and we're going to check that by doing an integration. To show that the area under the PDF is 1, what we need to do is to integrate the PDF here from t equals 0 to t equals t tending towards infinity here. We don't need to integrate the region for t less than 0 because the probability function here, the PDF, is 0 for any value less than 0. So this is what we've got to show. So this is a fairly straightforward sort of a thing. You might want to pause the video and just make sure you can do it, but here it is in case you're not feeling like doing that. So what we're going to have here, I think I've just dropped a little lambda there, which wasn't great. So we're going to have e to the minus lambda t here, and then we're going to need to divide by minus lambda. And there are our limits. We can, of course, cancel the lambda, and we're going to finish up with is minus e to the minus infinity, minus minus, but then that's going to bring it to plus e to the 0. Now, hopefully we know that e to the minus infinity, well, that is going to tend to 0. And we should hopefully also know that e to the 0 is 1. So there we are. That was what we were requiring to do. So we've shown that the area is 1. That completes our first video on the exponential distribution. The next video is on calculating exponential probabilities and also the cumulative distribution function here for the exponential distribution.